Okay, hey guys, a very good evening. We are going to start on this new session from Unacademy programming. It is going to be problem solving on shortest path algorithms. So, you all have probably got acquainted with the shortest path algorithms. You will find one of my videos which is on Floyd Warshall. And some of my videos on Dijkstra and Belmont-Ford, I think you might find them on Unacademy. I don't remember. Anyway, uh, we using our knowledge of those algorithms, we'll see how we can solve medium to hard problems on that. Easy, medium, hard problems, we'll be looking into them. Okay. So before we proceed to our problems, let us first get ourselves acquainted with the algorithms once. Shortest path algos. So it will be a brief kind of a revision. The first algorithm in this shortest path algos, the first algorithm that we all study, I hope you all will be able to tell, it is basically BFS. BFS is the algorithm that we all study. So whenever you have got you have a certain source and you have to see which are the points you can reach, and for every destination you have to find out how you can trace it back to the point, we use BFS kind of a thing. BFS is basically a breadth first search, which is that you start at a point, then along the breadth you basically proceed, which means that find out all the neighbors for a certain source, find out all the neighbors which are at a distance of 1, then find out all the neighbors which are at a distance of 2, and so on, something like this. So a characteristic feature of BFS, whenever we discuss it in the realm of shortest path algorithms, is that it does not involve edge weights. So no edge weights are involved. Okay? No edge weights are involved. And then we see that it takes around order n plus m time, something like this, where n is basically the number of nodes, m is basically the number of edges. So I hope this is a very normal terminology. There's a number of nodes, and m is going to be used furthermore like ahead as the number of edges. We are going to use it. Now, no edge weights are involved. In that case, we can use BFS and it will work in a good amount of time. The second case is, but again it is meant only for single source. What about if we have multiple sources? We can have multi-source BFS, and with multi-source BFS again, our total time taken will be order n plus m. So we can have, this is just a different paradigm which you might have seen, multi-source BFS, which we won't be requiring today for today's problems, but it's good to keep in mind that if you have multiple sources and if you have to visit like all the destinations, you have to find out that for all the destinations what is the shortest path from any of the sources. Then basically you need to use something like order n plus m. I hope you all can hear me. I didn't ask you because it seems that you all can hear me. So anyway, after that you basically encounter Dijkstra, which comes after this. Dijkstra basically does the same thing. All of these BFS, Dijkstra, they all use greedy methods. What Dijkstra does is it greedily chooses the next node which is at the shortest distance from the connected component, the current connected component, and it will update all the nodes at every point of time. This, you might remember, it runs in somewhat m log n time, something like this, e log v. You might remember this. We have Dijkstra and we have Belmont-Ford. In Belmont-Ford, we remember that the main advantage is that we can handle negative cycles. We can detect negative cycles. Other than this, we know that after every iteration, the first, suppose I am at first iteration, so I know at the end of the first iteration, I will get the first neighbor of, or the first level neighbors of, the source vertex. So if there is a source, I'll get the first level neighbors after the first iteration, the second level neighbors after the second iteration, and so on. Now this algorithm does not work in that manner, but eventually we get something like that. And fifth is Floyd-Warshall. Fifth is Floyd-Warshall. Floyd-Warshall actually solves the entire thing using DP, and for this, the advantage is that we get the shortest path from every point to every point. So from every I to every j, we find the shortest path. So this gives us actually the shortest path I to j for all ij. Make sense? So these are basically the 5 shortest path algorithms that we are concerned about. Usually multi-source BFS is not treated as a separate algorithm in shortest path algorithms. I've mentioned it because just to remind you all that how we can handle multi-sources, multiple sources together. We can use it. Multi-source Dijkstra can be also an option. We can use those things. But Floyd-Warshall does the entire thing in order n cube time. And see over here in multi-source BFS, there's a we can say only for the people who are not the sources. In multi-source BFS, we are not finding from multiple sources to all the destinations. We are not finding the shortest path from the multiple sources to all the destinations. We are choosing that particular source which is nearest to the destination. So multi-source BFS don't think this will solve for multiple sources. But considering that there are multiple sources, it will tell us the distance of every destination from the nearest source. So that is multi-source BFS. But if you want to consider that for all sources, I want the distance to all possible destinations, then we will look at Floyd-Warshall. Okay. So Floyd-Warshall, on this I have taken a session, I think 2 days back. You can go and watch that if you like. Today we'll be using it like a black box, or to some extent we'll also be discussing the working, because in one of the problems we'll be requiring that. But yeah, I think this much of introduction was necessary. If you have any questions in regard to any of this, you can ask. If any of this you have any question, and we discussed in our last session that Floyd-Warshall also helps in detecting negative cycles. We discussed it. So negative cycles can be detected using Floyd-Warshall. If you have any other question, you can ask. Maybe before starting we can discuss it. Else we can start. No questions? Okay. So let us just keep in mind these 3 algorithms for today: BFS, Dijkstra and Floyd-Warshall. We'll try to use these 3 algorithms and we will see how it fits in, how the algorithm fits in our purpose. So the first algorithm that we'll be seeing is from Online Judge. The problem is page hopping. I hope I'll be able to get that. Yeah, there it is. So maybe I can show you in this version. Okay, it's already downloaded. P821 downloads P821. Yeah, there I go. So this is basically the problem. I can share you the link. You should be able to get the link from here. I don't know how to share. So you can find out page hopping over here, and here is the problem. I'll be scrolling it down. First read the question. I don't think you require the sample test cases, but anyway, if required, I'll share it. So read the problem first. This is an easy question. This is a warm-up question. Just to ensure that you all can recall the algorithms properly, this is the first question. I will start reading the question from 6:11. I'll explain the question at that time. Till then, please read the question yourself. At 6:11, I'll explain the question and then come to the approach. Till then, you can read the question and you can suggest your own approaches. We can have a holistic discussion involving all approaches. Okay, so what it says is it first introduces you to the real world, scope of the problem, that if you have to go from any page to any other page. Now see, when you have hyperlinks, in the backend there is some particular manner in which they are located. So if you have to shift from one page to a certain page, it is not always feasible to maintain one-to-one, linking. So it often takes place through through certain pages. So it says that only 19 clicks are necessary to move from any page on the World Wide Web to any other page. Suppose that this is the case, that it requires 19 hops. So what it says is that you have similarly a graph and you may be at any of the nodes. From any node you have to visit, suppose any other node. Suppose you have to visit from 2 to 3. If you have to visit from 2 to 3, you require 2 hops. The distance is 2. If you have to visit the other way, 3 to 2, then also it does 2 hops, 1, 2. From 4, if you have to visit 2, you have to go 1 step, 2 step and 3 steps. You have to go 3 steps. Now we are only asking that for all I to j, from any source to any destination, such that we are not choosing the same source and destination, they have to be dissimilar. So between any source and destination, what is the average path length? What is the average path length? And it has shown you the computation. It said it first computed the lengths of all the paths and it just did the average. The sum of paths divided by total number of paths. So we are only concerned about the shortest paths. So how many pairs first of all are there? There are n source vertices and for every source vertex there are n minus 1 destination vertices. We know that. So basically the denominator is n into n minus 1. This is the first step. Now what can lead us to this answer? What can give us the average, shortest path? Usually CodeChef nowadays does not give, directly this kind of a question. CodeChef still maintains different varieties, but this kind of question, if it comes in Codeforces, you can expect it in, I think, in div 2, it can come in maybe B. In B you may get it, and then yeah, div 3 it can be more common. You can get in CD, div 3. You can even get it in C, but there are less chances in div 2. How can we solve it? This is pretty straightforward, but let us try to understand the, try to think about all the shortest path algorithms and think, if I apply Dijkstra, how will it work? If I apply BFS, how will it work? And so on. Apply something like that. I'll be starting at 6:16. I'll be starting the discussion. Till then, please let me know if you have any approaches. We can discuss them here. Otherwise, I'll start at 6:16. This is a warm-up question. I won't be spending any time. But if at any part, if you have any doubt, please ask me. We can elaborate on that. But we'll be more, interested in the next questions, where we have to strain our heads even more. Over here we just need the sum of the shortest paths. Remember, sum of the shortest paths. So from 4 to 3 or maybe from 4 to 3 I can have a path of length 5 as well, where I'll visit from 4 to 3, then 3 to 1, then 1 to 2, and then 2 to 4, and then 4 to again 3. But I'll not take such a longer path. I will take only the shortest path from 4 to 3. अभी तक आपके चैट्स शुरू नहीं हुए हैं. You can think of like starting to type at least, so that the chat starts at some point. As it would seem that I'm speaking to a wall. Anyway, one more minute. Your approaches or anything, whatever you've got to say. If it is very easy and you want me to just move away from here, you can tell me that. Or if you think it is very hard, you want me to discuss the approaches, you can tell me that. Whatever you want. Because at Unacademy also in my classes I do the same thing. I always try to keep it student centric. How the students want it to be understood, how the students want it to be followed, I try to follow that particular way. So you can definitely. Okay, fine. So let us start with our approaches. Where are we? I think over here, right. Let us start with our approaches. We have to find all the shortest paths. We have to find the sum of all the shortest paths. And okay, I did not show you the constraints, but constraints are not given as well. Okay, maybe here it is given. Page numbers will always be in the range of 1 to 100. So there are 100 unique pages, right? So what can you say? Easily you can say that up to n cube or up to n cube log n or up to n cube root n you can run things. So you can say, first of all, using Floyd-Warshall, I can easily find the shortest path from any a to any b. From any a to any b, I'll be able to find the shortest path. So what can I say? After doing that n iterations which we used to do, what will I get? Something like this, that there will be n columns and there will be n rows. And which are the cells which I'm not interested in? I'm not interested in these diagonal cells. Why? Because here the source is same as the destination. You have V1, V1. You have V2, V2. You have V3, you have V3. And so on. Right? So what can we say? That these are the cells we are not interested in. So what will we say? And we know that these will be 0. We know that these will be 0. Because there are no such negative cycles. I think this much we covered. So these will be 0. So if these are 0, I can simply say just ignore these diagonal cells, whatever you have, and read the rest of the cells. And what is going to be the rest of the number of rest of the cells? So we'll basically divide this sum by n into n minus 1. So where n is the number of vertices, I can say n into n minus 1 is the number of valid paths. How can I say from this diagram? I can say the total number of cells is n square and the number of cells I'm not considering is n. So it is again n into n minus 1. So I can just use this as the denominator to find out what is the average value for any of the paths. So it is the directed graph, hence we cannot consider ij to be the same as ji, and hence I've considered them separately. Now, which other algorithm can we use? Among BFS, Dijkstra, Bell-Manford, which other algorithm can we use over here instead of Floyd-Warshall? Can you identify? In this question which I shared, I think I should mention it somewhere for all the people who are joining new. Basically this is the question, page hopping question which I shared. So in this question, instead of Floyd-Warshall, which gives me all the paths, what is another algorithm that I can use? I have to find the average of the shortest paths between every pair. That is basically what it comes out to me. So I can say this algorithm, this pseudocode will basically look like something like this. First I'll say I'll have all the values, suppose from 0 to n minus 1. Then I'll say I will have dpij or dp you can say nn, where they all contain infinity. They are all filled with infinity. Then I'm going to say for int I equals to 0, I less than n, I plus plus. This I will serve as the intermediary node. This I serves as the intermediary node. And then I'll say before this I'll definitely, okay, before this I have to store the edges or the edges, I'm sorry, the edge lengths. Okay, the edges basically I'll be storing. So only the edges I'll be first of all containing, which can be the adjacency matrix, you can imagine. So we'll start with the adjacency matrix. Then we'll basically run this algorithm for int j equals to 0, j less than n, j plus plus. This is going to be my source node. Okay, so this is my source node, SRC. And then for all the destination nodes I should do the same thing. So k equal to 0, k less than n, k plus plus. What shall I say? Now that important line, I want to control, I want to find the optimized value of dpjk. So I'll have two options. Choose the minimum of dpjk. So whatever value is existing, either choose that or reduce that by some other method. Basically this method, dpji plus dpik. This is basically another method. Yeah, this is basically one method, and usually before this, in the actual implementation, before this it is checked so that whether these two exist or not, these two are valid or not, that is, they exist apart from j to I or I to k or not. Theoretically this is also not wrong, this is also absolutely correct, but you can have an overflow. If you do this plus operation, you can suddenly get an overflow. Then you will start blaming that, okay, I added, I followed this algorithm, I'm getting an overflow. The reason of the overflow is the data type which our computer is using, or the basically the limited. This is Floyd-Warshall. Yeah, so we are actually seeing this problem and we are analyzing this problem with respect to Floyd-Warshall. And now so this is going to be the core, and after this what I'm going to say is that just find out whatever you have, I think. Yeah, so for int I is equal to 0, I'll basically find out all the sum of all the parts, the sum of all the paths, I less than equal to n minus 1 I plus plus, and I'll say that similarly carry me for all the destinations. So from all sources to all the destinations, we will say that if I is not equal to j, and we know even if I is equal to j, dp of ij will be 0 only. So we can say just sum plus equals to dp ij. You can use that. If I not equal to j, you may not use that, right? And then we can say just divided sum divided by equal to n into n minus 1, but in that case we require double over here, so this has to be double. So this is straightforward, finding the average shortest path using Floyd-Warshall. What other algorithm could we use here? Could we use Dijkstra? Could we use BFS? Could we use Bellman-Ford, keeping the complexity same? So I'm interested in keeping the same complexity. So what else can I use? I don't want the complexity to increase. So the key idea is, you can see that all the edges are costless. They don't have any edge costs. They have cost 1. You only need the number of edges to decide the path length. The cost of the edge is not there. So whenever every edge is basically uniform, it is of cost 1, or basically if the cost is not a factor, we say BFS is better than Dijkstra. We definitely don't need to spend time behind Dijkstra. BFS is better. So we can try to use BFS. Let us see what we get. If we use, just a second, I'll mute it. Yeah. If we use BFS, what shall be our time complexity? We will do BFS for all the sources separately. We can do for all the sources separately, so it will be order n plus m. And what is m? M can go up to n square. It may go up to n square. So we can have this equal to order n square for every node, for every source. So for all the n sources, we will have total of n cube. This is for all the sources, right? Can we use multi-source BFS? No, because multi-source BFS will tell you that these are the multiple things. What is the, like for each destination, what is its shortest path from any of the sources? So you cannot use multi-source BFS over here. So this is the time complexity, and you can see it is the same as our Floyd Gaussian. So you can directly use BFS also. If it is like whichever is easier to you, you can use that. Make sense? And for Dijkstra, you basically will have an extra thing of log n. So you can again do m log n multiplied by n. So it will be n cube log n. So that's it. Bellman-Ford is not apt for this kind of a test case. So this is any doubt? Now we'll be moving to an interesting problem. Before that, do you have any doubt? Okay, I guess no, because this was just for revision purpose. Let's start the next problem, and that is, let me check. Greg and graph. Yeah. Yeah, this looks fine. So you can search Greg and graph on your laptop, or you can basically check the question over here only. This is the question. At 6:29, I will scroll down to show you the test cases. Till then, read the problem very well. The problem name is, I think, Greg and graph, right? Greg and graph. You can check it in your own laptop as well. Okay, so the question says it has got n steps. So first of all, it has got n vertices, and it is a weighted directed graph. Weighted, that means no chance of BFS. Directed graph. Directed means I to j is not the same as j to I. So now what will be done is, on the ith step, vertex number xi is going to be chosen. So you'll have n steps, and what values will be chosen? These vertices will be chosen. Okay, you have been given this in the input. In this order, they'll be chosen. Can we consider deleting node as intermediate for calculating sum before deleting? Interesting. Think on it. Very good. A very good approach. So the question is that first we'll be removing x1. Before that, we'll be telling that whatever is the shortest paths among all the vertices which are located in the graph, tell me the sum. So I'll require the sum of all the shortest paths. I think sum, right? Sum of lengths of all the shortest paths. Then I'll be removing x1. After removing x1, I'll ask, what is now the sum of all the shortest paths? Okay. So after remove x1, I'll say that x1 is removed. All the edges with x1 are removed. Now n minus 1 vertices are there. What is the sum of shortest paths? Then I'll remove that x2. I'll remove that x2, and I'll ask that among the rest n minus 2 vertices, what is the sum of the shortest paths? And up to xn. So when I'll remove xn, I'll basically, after that I'll have 0. So yeah, these are the test cases. First we are saying what is the number of vertices. So this is the number of vertices. Then this will tell us basically the edges that are located, I guess. No, this will tell us the adjacency matrix. So we'll have the adjacency matrix, something like this. And not just the adjacency matrix, they contain the cost as well. So it contains the cost. So whichever edges are not present, it contains 0. Whichever have like the presence of the edges, it will have some non-zero cost. Okay. Okay, so no, 0 represents that it is the same thing, and it will always be, it has told you it will always be from 1 to 10 to the power 5. So don't think about that case. So there is a connected, like it is sort of every node is connected to every other node. And when we talk of edges, yeah, so this is basically an adjacency matrix. So the first row tells that from the first vertex, how many you can reach, or which are the people you can reach all of them. What is the cost incurred to reach each of them? What this tells is, before deleting anything, I'll get 9 as the sum of shortest paths, and after I delete the first vertex, which is 1, I'll get 0 as the sum of the shortest path. Then I'll say that before removing anything, I'll get 17. After removing a certain vertex, I'll get 23. How come? How come it increased? Basically, the vertex which was helping in creating a shorter path between two other nodes, that got deleted. So between those two nodes, now we need a longer path. So that is the reason this got increased. And even this 404. This 404 got created because from between them, we removed a smaller, a vertex which could have shortened the path. Something like that. So yeah, the first one is before removing any vertex. Second one is before removing the second vertex or after removing first vertex. Third one is after removing second vertex. And fourth one is after removing third vertex. Make sense? That is it. So what can we use? If we just use Floyd Warshall, if we say we require the sum of the shortest paths after every step. So every step we'll use the Floyd Warshall. Every step, if we use the Floyd Warshall, it will be basically when we have everything n cube, when we have deleted one vertex n minus 1 cube, and in this way I'll be proceeding. So in this question, which is Greg and graphs, if I approach in the trivial manner, which is n times Floyd Warshall, what will I get? N cube plus n minus 1 cube plus n minus 2 cube plus dot dot dot. and it comes out to be something plus dot dot 1 cube at the end. It comes out to be something like this, n into, I think, n square, n plus 1 whole square by 2 square, I guess, something like this, right? I don't exactly remember, but it was something like this, right? So we will have basically these many computers, which is order n to the power 4 for sure. Here it can be a little bit here and there, but it will be definitely order n to the power 4, right? This was sort of like, we know this is going to be the complexity, and we know n is 400. Okay, I'll mention over here, this is a CF problem. N equal to 400, so we can say that, I think it was 400, right? Or 500. So if it is 500, we cannot endure n to the power 4, because n to the power 4 is going to give us something like this, 5 to the power 4 into 10 to the power 8, which is quite high. We cannot end this. So how can we ease this process? How can we, rather, like every step, how can we optimize it? Let's try to visualize the last step. What is the last step? In the last step, we say that only xn is there. So see, in the first step, we have everything. We have x1, x2 up to xn. In the last step, in the second step, we have x2 up to xn. I have removed x1. In the third step, we have got x3 to xn. Okay, I have removed x2. And similarly, at the last step, what do we have? Xn. So what can we say? Can we think it in this manner, in this direction? That over here I have taken one vertex. For this one vertex, I can find out that keeping this, like for when it is one vertex, I know it is pretty easy. Because if there is one vertex, then I won't basically have anything. As I move ahead, I'll say whichever vertex you are introducing. Why did I say in xn you will have nothing? Because its xn is the only vertex. There is no other vertex, so there is no other edge. So shortest path is always going to be of length 0. Okay, sum of shortest paths. So this is a trivial case. As I will add this xn minus 1, can I say that now the only addition is xn minus 1. So whatever vertices you have, whenever you are introducing xi, can we say that whatever vertices you have, try to revise their shortest paths among themselves, taking this as the intermediary node, and also try to find out what will be the distance of this from all those vertices, the smallest one. We know we can find it easily. In other words, what can we say? That let us suppose that from the very beginning, at this step only, we have all the vertices. Let us suppose we have got all the vertices, and let us find out the shortest path with only xn as the intermediate node. Okay, then I'll find all the shortest paths. I'll revise it using xn minus 1. I'll use xn minus 2, and hence after some iterations, what will I have? I'll have only xn minus 1, xn minus 2, up to some stage, suppose xn minus 3. Now what will be the condition of that DP table? That will tell me all the shortest paths which are possible using only any of these as the intermediate nodes. So can we say this satisfies our requirement? So when we are left with only these nodes in the fourth step, will be required, we will retain only this requirement that for these 4 nodes I need the shortest paths among these things. So can I say that when I'll be calculating the shortest paths, the intermediary nodes also must be within these. So can I say that now I know my intermediate nodes will be between this, but I don't know whether my extreme nodes will be in this or not. So if I choose I and j such that they lie over here, if I choose something like this, in a set I'm maintaining what are the current vertices. Suppose this is S, this entire thing is S, this entire collection, this entire box is S. So I can say for I in basically this S, for all the I which are in S, and for all the j which are in S, I'll basically add them, sum plus equals to dp of ij. Can we say something like this? And then what shall we get? We'll get all the paths, all the shortest paths from every node which is in our set to every node which is in our set. And we'll also ensure that the intermediate nodes are also contained in our path. The moment we are able to do that, we can say that yeah, now what do we need to do for this? For this we can say we just need to do a simple Floyd version. Just a single time Floyd Warshall. We'll start from here. The only requirement is now our xn minus 1, we have to basically sort in this manner. What we were doing typically like 1, 2, 3, 4, 5, 6 in that order in Floyd Warshall. Now our intermediate nodes have to be taken in this order: xn minus 1, xn minus 2, and so on up to 1. This shall be the order. Makes sense? So this actually requires a very good understanding of Floyd Warshall. If you understand the steps of Floyd Warshall, then only you can understand this well. So if you think you have some doubt, you can go back and watch my previous video, which you will find it was on Floyd Warshall specifically. I have described how this, Floyd Warshall reaches the result. I did not get some part. Okay, it has to find actually the sum of all the shortest paths, right? So, so currently, suppose what you have done is you have revised your DP, saying that this can be the intermediary node. Now after you have done that, you have to say, now that I have introduced it, we are moving backwards, right? So when you have introduced xi, then you need to find out this thing. The sum, need to know the sum of the shortest paths between all pairs of the remaining vertices. Okay? Before executing each step. So before you delete xi, you have to find this out. That is basically to say that after adding xi, you can find this out. Make sense? And for summing up, what do we need? We need something like this. Suppose at the end, the last three vertices, suppose they are something like this. Xn, suppose it is equal to 4, xn minus 1 is equal to 3, xn minus 2 is equal to 5. So what do we require? We need to know dp of 4 to 5 plus dp of 4 to something like that, right? Right, 4 to 3 and so on. We'll basically say 4 to 5, 4 to 3, 4 to 4 is not there. Then we will say 3 to 5 and 3 to 4. Then we will say 5 to 3 and 5 to 4. So these are the 6 things that we can do. The 6 steps will give us the sum. And what can we say? That if we maintain a set of all the vertices that we are taking, where the last element will basically be xi. In the ith step it will be xi, something like that. Yeah. Then if that is xi, then you can take something like jk. Okay? Jk. So j and k, which are the 2 elements that you are taking in your Floyd Warshall as a source and destination, they must be over here. Because for the other elements, I don't care how they are reaching, where they are reaching. So I'll say j must belong to this s and k must belong to this s. If they belong, then I'll basically add the dp for I to j. Sorry, for j to k. Right? I changed the terminology basically because I took xi over here. It makes sense, right? So this is one of the best problems that I've encountered on Floyd Warshall, for which you need to know Floyd Warshall well. You cannot use it like a black box. Okay? Yeah, sure. Like I like the approach. I like that you were able to think in that direction. And yeah, with practice you can actually later on you can get the clarity. So anyway, let us move on to the next problem. Before we finish, I think we can cover another problem, even if not wholly. Maybe this is our third question. It will be an E problem, shortest path. Shortest path is going to be our problem from CF. Okay, let us search it. Code forces shortest path. Read this problem, we'll have a short discussion, and it will be better if you can read in your laptops, because I'll be shortly showing you the batches which are being offered at Unacademy. I need to show that so that you stay updated. So you can take a screenshot or you can open the link in your laptop and you can see that. Okay. At 6:48 we'll again start the discussion. Till then I'll be telling about the batches, or 6:47 we can start the discussion. Till then, let me tell you shortly about the batches at Unacademy. Let me close this. Yeah. So these are the batches. You have Transpire. Let me move away from here. Yeah. You have Transpire, which is on your CS fundamentals, OSDBMS networking. You have Eklavya 3.0, which is a 7.5 months beginner course, and Brahmastra 3.0, which is for college or off-campus placements. Mahayuddha 2.0 is for advanced programming topics. So these are the durations. 1 month transport started on 20th July. Eklavya started on 21st July, 7.5 months course. Brahmastra 3.0 5 months course started on 20th July. Mahayuddha, it's a 2-month course, started on 20th July. Structured learning path, 1 subscription and unlimited access to all courses. You can crack interviews of top companies. You get the best coders of India's educators. In Transpire, you'll basically have these computer networks, RDBMS, DBMS, operating systems, object-oriented programming. So those who have joined recently, I'll be discussing the shortest path problem of Codeforces. So shortest path, you can search with this. It is from Codeforces beta round 55. Okay, don't run away. Before that, we have these things, and yeah, in Eklavya 3.0 we are going to cover the beginner level topics, then the intermediate topics, and then these advanced topics. Then we have Brahmastra 3.0, over where we'll be keeping the topic pertinent to the placements. All our classes will be pertinent to the placements. We have maths and puzzles, then sorting and searching, bit manipulation and backtracking, basic data structures. And you have string algorithms, advanced dynamic programming, graph algorithms, interview problems, fast and fan. And Mahayuddha, I am taking this batch currently. So I am teaching advanced dynamic programming. Then I'll be starting on segment trees. Then we'll cover advanced concepts of graph theory and mixed problem solving. It is only for advanced, programming. And yeah, these are some of your educators. You have live interactive classes, practice relevant problems, doubt support. And this is the pricing. 1 month 6,000, 12 months you have 33,000. So if you think of 6 months, maybe 12 months can be better than this. It depends on you. You can try maybe for 1 month and then you can come to 12 months. It is totally on you. But on top of these rates, you get a additional discount of 10% if you use my referral code Saptarshi 1729. On top of this, you get an additional 10% discount. Okay, that's it. So yeah, coming back now. At 6:48, we'll resume the discussion. Please read the problem well. Okay. How shall we do it, Sachin? But this is a very important problem for your coding exercises, for your coding contests as well as placements, whatever. Keep triplets in hash map. Okay, how many triplets are there? Greater than 10 to the power 9, right? It's greater than 10 to the power 9, right? Or you're talking of only these, okay, these k triplets, fine. Okay, I'll keep them in hash map. Basically, I think you mean hash set. So I don't see hash map being required here. So okay, hash set, I'm keeping it then. Then I'll be traversing the graph with that. Right, it is not. So I took it differently. Okay. What we'll be doing then? During traverse, just a second. During traverse, I can check my parent and child node belongs to triplet or not. Then, okay. Now, will you fix it that for a particular node there will be a particular parent? Or will you say I'll consider multiple parents? Should you fix the parent or should you consider possibility of multiple parents? Will fixing the parent give you the correct answer, the shortest path always? It makes sense that you will stop traversing that path. Okay, okay. Yes means which one? Uh, yes means which one? You'll be storing for all possible parents or you will fix the parent? That this parent is nearest to me, so this has to be my parent. Are you going to be stubborn or are you going to be flexible? Don't like prefer not writing yes or no because I can't recall what was the question to which you are responding. So it will be better just write a short note maybe that I'll fix it or something like that. What about the rest? What do you think? Hard problem, easy problem, very easy problem, cakewalk. What do you think? Or how to approach? Forget the difficulty level. Sometimes if we can approach, we feel very good about it, right? Always solving it entirely is often not the ambition. It varies across people, but often in computer programming we feel that okay, if we are able to solve it to some extent, it appears like very nice to us. Just think about that. If you are asked in the interview, sometimes questions are asked so that there is 99.9% probability that you can't reach the correct answer. But whatever partial things you speak decides who is going to be hired, you or your friend. So it's all okay. Let's come back. I will save parent during traverse for current node. Can check child node for further visiting path. Let us see this. Suppose you have to reach n. So here over here, you have seen 2. Then you have something like this 3. And then you have this 4. And you have something like this. You have to reach n. And you know that this is going to be basically 100. And this is also going to be 200. This is going to be 1, 2. This is going to be 5. But you know that 2, 3n is not a valid pair. Okay? So how will you proceed? If 2, 3n is not a valid pair, according to your algorithm, what happens is when you come to 3, you have already decided that I should come from 2 because this is a shorter path. Some way, right? You might decide that okay, 2 is my parent. So if it is my parent is equal to 2, then what will you say? I can't proceed from here. So it will break this path. Then the thing is, like, suppose this path started from here. Suppose this is 11 and it started from here 1 and it went to the entire way. Will you discard this entire path? Will you discard this entire path? First of all, how are you choosing that which path will be going from this one? If from one you have got multiple paths, how are you choosing which path will be going? And if you are choosing it, if you are going up to some part and you are seeing that this triplet is not matching, will you discard this entire path from starting from here to the entire, like to the end? What about the rest? What do you think? So at 6:55 or 6:56, I'll be starting my discussion. Maybe 6:56. Till 6:56, please tell your own approaches because in the contests or in placements, you will be sitting, not I. I will not discard that path. You will not discard that path. Then which path will you discard? And first of all, what choice are you making? What algorithm are you applying? Are you applying any algorithm? If you don't know what is the name of the algorithm, are you applying anything greedy, anything DP, anything which takes case of all possibilities, or you're taking some greedy choice? If I would say that there is no such triplet, no triplet exists, which algorithm would it be? Simple BFS. First of all, you have edge weights, I think. Okay, there are no edge weights. Okay. So there are no edge weights, fine. So you can have multiple, right? BFS, okay. DFS. DFS can have multiple possibilities, right, bro? You have something like this. Suppose here you have 4 nodes. Here you have 4 nodes, each of which is connected to all the nodes. Okay? And here you have again 4 nodes, here you have again 4 nodes. So can you imagine how many paths are there? Suppose you have 4 into 4, 16 paths over here. So basically it comes out to 16 to the power n by 4. So n by 4 compartments are there, and n by 4 minus 1. 16 to the power n by 4 minus 1, this is the number of paths possible. If you discard an entire path starting from the origin to the end, if you discard an entire path, that is a bit of a problem, right? There are so many possibilities, first of all. Let us still try to think on your approach. What you are saying is, I start from a node, I write the next node, which is like I write all the neighboring nodes. Then I will write whichever nodes can be my 2-level nodes. Okay. Okay. If a contradiction occurs over there, complexity are same for both. Okay, BFS and DFS, both of them. No. For DFS, if you have to find the shortest path, complexity will never be the same. For DFS, you can say that if you require, yeah, you'll be updating distance vector for each node. Whatever you do, if you do DFS, then the problem is you have to revisit the nodes. If you revisit the nodes, then it is overlapping of subsequences, the complexity won't be the same. But if you use BFS, then let us analyze it. This is, suppose this triplet is not allowed. And you will say, I will choose a bigger one now. Something like this. So you have this going to here as well. This one you do already have. This is interesting, quite interesting. These are a distance. Okay, so you first decide this path, then you are telling that now this cannot be the path. So I will try from everything that I can from here. You will try everything from here and you will try to reach it. If you take complete graph, is it a complete graph? It is not a complete graph. If you take complete graph, what is going to be the situation? So one thing is good. In your algorithm, you are considering every vertex at most once. You are visiting every vertex at most once. If a violation occurs, you are not at all visiting it. That part is good. Yeah, it should work. It should work. So you can try that algorithm. The approach that I immediately got when I read the problem, and which has definitely worked as well, was that for every node you maintain for all the parents who are visiting it. For every node you maintain that. So when you maintain that, okay, it's basically the same thing. Yeah. So this is the right approach. You just have to implement it. So how you said, suppose this is A, and suppose you have visited B, and then you visit something like this C, and suppose ABC is not matching. So now you say I can't try this I cannot try this. Okay, but there is something that while you are doing this ABC, there is something that B to C, there are certain things. So C is located at a distance of A if it comes after B, and if it comes after this guy, then it is located at a distance of 1 2 3 4. Or if you take 3 over here, then basically it comes after 1 2 3 4 5. So over here it is 5. So these are like two different things. According to the parents, your distance from the beginning is increasing. Okay, so you can either choose, like if you do a BFS in that manner, yes, you can do that, or else you can say that since like you're considering various possibilities, so yeah, can you name adjacent of B? Yeah, D, right, D E F. So you'll basically do something like this, GH. What you are saying is something like this. I'll first choose A, then I'll choose B and D, then, and these are all undirected, I think, or directed, two-way. So these are undirected. So forget about these arrows. These are all undirected. We can see we'll have ABD. Then I'll try with C and D. I can take DBC. Yeah, we can take DBC, right? We can take DBC from here. So what I can say is that, so what will you say? That even if a vertex is visited, you will still visit it. Think about it, that a vertex B has been visited beforehand. For B you could not visit C, you can visit something else. You can get many other things over here. In BFS you should first check the neighbors. So you may face something like D1, D2, something over here. So what will you say? That due to D I'll remove B from here and I'll take B after me. See, if you take B, then the problem is that due to B you again have to take all the children of B, which is D1, D2, D3. So that means for B you are repeating all the things. For B you are repeating all the things. Okay. So you cannot just repeat, you cannot do that single thing. Because you know till now that after B, C cannot be there. You don't know whether B should be excluded or not. It may happen that B should not be excluded, but when you are doing BFS, you are proceeding along the breadth. So that is why we cannot suddenly cross out B. We know after B, D1, D2 is going to come. Something like this. We know after A, we are getting B, we are getting C over here. After B, something D1, D2 is going to come. It may happen that D1 will lead us to, forget this arrows, D1 will lead us directly to something like D. It will lead us directly to something like D. But if I have something else, C might lead to X and X might lead to D. So I cannot, just by seeing that B leads to C, I cannot say. Okay, I have to repeat if I have only one path like DBC final node. Okay, you can try coding it. One other solution can be that for all these vertices, you can do something like BFS. Do BFS, but do mention that for every vertex that you're visiting, if you have parent 1 as the parent, if you have some vertex pair 1 as the parent, then what is going to be the distance D1? If you have pair 2 as the parent, then what is going to be the distance D2? If you have pair 3 or pair I, what is going to be the distance Di? If you have this in a table, then this will sort the work for you. So now when you will try to do I to J, you can say that if pair 2 to I to J is violated, if that is a triplet, if it is a triplet pair 2 to I to J, you can say directly that this is, like for this J, we have to take some of the other cases. I have to choose from these cases, like from these D1, DI. Okay, I cannot choose D2. From here, I'll choose the minimum. So in this way, for every vertex, there is how much of storage? Basically, it should be like the number of storage should be according to the number of edges, total number of edges. So total storage is 2 into 10 to the power 5, not 3000 whole square. And that's it. So total number of checking will be in something like this. So whenever you are trying to decide between j and I, you have to find out through some priority queue kind of a structure or through some set kind of a structure that what is the lowest one. Whatever is the lowest one, you'll take that. You can always take that, right? I think I'll have my implementation. You can maybe have a glimpse. It is 3 seconds. Yeah, okay. So maybe we can have a glimpse. I think I did code it. Okay, let's see. Yeah, shortest path. So what I have done is, this may not be the best implementation, but what I'm simply doing is that I'm proceeding through these pairs of parent and the current value. So this is just the first thing, the first when I'm visiting the first vertex. Later on I'm saying that this is going to be my pair, which is B, that is the parent, and then the adjacent node of B. Then I'll say whether that has already been visited or not. If it has already been visited, I will not revisit it. Okay. So if it has already been visited, then only I will, like, if it has not been visited, then only I will process all of these things. Then I'll say that if ADJ, BJ, you can find it in my submission also. Today only I coded it. Today afternoon only. So if B to J, this is N, the adjacent is, that is B to J, this is N. What does this mean? That you have already got the nth one. And since you have got by BFS, you know this is the shortest path, you can just break it and you can form the path like this. So yes, DFS was correct, but just think about it, how you will be prioritizing what you will be storing. I have taken some space, some extra space. You may choose not to take it. It's up to you. So how many possibilities are there? The number of possibilities, how many values are going to be there inside this queue-like structure which I've used, this pairs. There can be n square. There can be n square, which is 3000 square. So I'm using some good deal of size. You can maybe shorten on that. It will be basically m. It will not be just that thing. It will be 2m, maximum 2m. Okay. So we'll be able to solve it like that. Over here, I'm just storing it in a hash map. What kind of triplet I don't like, that kind of a thing, so that I don't have to use some hash map and then a hash set and those things. I'm storing a kind of, okay, I'm storing basically in a hash set. What is the string that I don't want to come? A plus space plus B. This is also a bit inefficient, but I wanted to code it faster. That's the reason I coded it this way. So yeah. And path regeneration is easy. In BFS you can do it very easily. So does it make sense? Had cost been given, then also we could have done it using exactly this process. We could have directly used this process. We just have to add, like, instead of doing, I think, distance over here, or we are not doing the distance because this is simple BFS, we don't need to store the distance. We could have just stored the distance with each of them and we could have got it easily, right? In Dijkstra, we would just have to maintain that red black tree or priority queue kind of a structure. It would have done our job. That's it. So I think you can try this problem. You can try running this in your own way. There might be many solutions. So okay, if there are no doubts, maybe we can call it a day. Try to solve it, try to submit it. It will complete this session. And yeah, so take care and hope you enjoyed the session. Do let us know what kind of sessions you'll be looking for in the next classes in the comments or wherever you can. I'll try to align it in that direction. So yeah, take care. Bye.